Quite often, if you're looking for a type of function that a sequence of functions rather, that converges with respect to L2 but not another way, or converges another way but not with respect to L2, you can find an example you want by looking at spikes and tails. And so what I mean by this is that by spikes, consider a function that looks like 1 over x to some power alpha on the unit interval, so near 0, where you have a spike, right? And then by a tail, consider looking at some example of a function like 1 over x to the alpha on a domain like 1 to infinity. So these are sort of classic ways to look for something that might converge or diverge depending on what particular alpha that you chose. And we know, for example, that alpha equal 1 is sort of the cutoff point for where these integrals of this type converge or diverge. And for L2 convergence, we're looking at integrals, right? So for this, I'm going to look at sort of cutoff versions of spikes and tails. So for this, I'm going to use this notation. So the characteristic function of a set. So the characteristic function of a set A, and we'll denote this with a chi for a characteristic, the Greek version of ch. So the characteristic version of A is 1 if x is in A, and it's 0 if x is not in A. So, for example, the standard unit step or Heaviside function, which is 1 for non-negative numbers and 0 for negative numbers. This is the characteristic function of the interval from 0 to infinity, right? And if we look at, say, the characteristic function of the unit interval from 0 to 1, let me just graph it here real quick. It would look like this. And since I'm including the endpoints of the interval, I guess these are solid dots and these are hollow dots. Okay, so there's chi of 0, 1. Okay, so let's see. Let's consider the sequence of functions u sub n defined by, and we'll take 1 over square root n times the characteristic function from 0 to n. So this will give us a family of tails. And you see that if you start to graph these things. So if we take some axis here, let's graph u1. So u1 is just going to be the characteristic function of the unit interval that I just drew. Whoops. And even though the vertical part is not really part of the function, I just draw it because it helps with the visualization. So, and that was u1. So for u2, it's going to be 1 over the square root of 2 times the interval now from 0 to 2. Okay, fine, be crooked. And then for u3, we've got 1 over root 3, and let's see, that looks like maybe 3 units there. Whoa! Somehow it gave me an ellipse. What the heck? And so forth, right? So you get the idea of how things are going here. So let's look at modes of convergence for these. So Pointwise. Does it converge pointwise? Well, to check that, we fix an x, and we're going to look at, I didn't specify, but I should have specified that we're looking at the interval from 0 to infinity, and we're going to check to see if this sequence converges to the 0 function. So if we fix an x in this domain, 0 to infinity, then eventually, so no matter which x you choose, it'll be the case that for a large enough n, the support of the function, meaning the part of the function which is non-zero, so here it's 0 to 1, here it's 0 to 2, here it's 0 to 3. Eventually, this purple region where the function is non-zero will be big enough that the function value at x is positive. And at that point, un of x will be 1 over root n. And so after that point in the sequence, the terms look like 1 over square root of n, 1 over square root of n plus 1, 1 over square root of n plus 2, and those things have a denominator which is blowing up, and so the whole thing is going to go to 0. Okay, and that argument can be made for any n, or sorry, for any x. So this, so un converges to 0 pointwise. Now let's check L2 convergence. So for L2, we're going to look at the magnitude or norm of un. And like I said before, it's easiest to work with actually norm squared, because norm squared converges if and only if norm converges. So this is the integral from 0 to infinity now of magnitude un squared in absolute values. And so the characteristic function part truncates the domain to be from 0 to n. And on that domain, our function is 1 over square root of n. And so what we end up with is we end up integrating 1 over n along the interval from 0 to n, and we get 1. Okay, so does the distance from un converge to 0? No. It turns out that the function un is a unit vector in this particular space. And the unit vectors do not converge to 0. They don't get anywhere close to 0 because they're bounded away by distance 1. So this does not converge to 0. So this does not converge in L2. So then we can talk about uniform convergence and whether or not it converges uniformly. And so we're going to look at the maximum of unx minus the thing we're converging to. We're looking at the 0 function. And so this maximum right here, this is going to be on that interval. The maximum distance that this function gets from the x-axis is 1 over root n, and it does that for any function. And so the limit of the max difference is 0. So the UNs do converge uniformly to 0. Okay, so we can contrast this with spike. So if we take UN to be something like n to the 1/4 times xi of 0, 1 over n. So here's something going spiky. Then let's see. So u sub 1 is going to look just like it did before as the characteristic function of the unit interval. and then u sub 2 is going to be, well, now we're just over the interval from 0 to a half, but we go up from up to a height of the fourth root of 2, so that's bigger. So it'll look something like that. And then we can go on and look at u3, and u3 is going to be on an even smaller interval. It only goes to 1/3, but now it goes up to fourth root of 3, and so forth. So you get the idea. So it's spiking out at 0. Okay, and again, we can look at the 3 different types of convergence. So for pointwise convergence, if we fix any point, then eventually what's going to happen is that the support of the function, so that again, that's from 0 to 1 in this case, or from 0 to 1/2, or from 0 to 1/3, or whatever, that portion of the function which is non-zero there, that's the support. So eventually it's going to happen that 1 over n is less than the point that we picked, and so for that it's going to be the case that unx is equal to 0, and it will stay 0 forever after, so it converges to 0. And so it converges to 0 at every point except, look what happens at 1. So now we actually included 1 in the domain, or sorry, not 1. Look what happens at 0. Look what happens at 0. We included 0 in the domain right here. If we look at x equals 0, then un of 0 is going to be n to the 1/4, and that one blows up to infinity as n gets large. So since this point is in our domain, it doesn't converge pointwise because it fails to converge at the point 0. So it doesn't converge pointwise. So you can see how sensitive the notion of convergence of functions is to the definition of the domain of the functions. Just that one point is enough to throw it off. So let's take a look now at L2. So at L2, in L2, we look at the size of un, and it's the integral from 0 to 1 over n now of n to the 1/4, and this is going to be squared dx, and so this ends up being square root of n times 1 over n, which is 1 over root n, and that guy converges to 0. So we have that un converges to 0 in L2. And if we look at uniform convergence, the max value of un, which is the same as the max value of un minus 0, and again, this is the max over for non-negative x's. This is always going to be n to the 1/4 because it takes that value at 0, and that one blows up. So with respect to uniform convergence, it diverges. So it does not converge uniformly. And so in retrospect here, you can see that these numbers that I was playing with, so for instance, having it be the square root of n on the interval from 0 to n for the first example, or having it be the fourth root of n on the interval from 0 to 1 over n. By playing with the powers of n and the lengths of the intervals, you can come up with examples for sequences which do or do not converge in L2 with spikes or tails. You can sort of custom tailor an example to suit your purposes.